So using a similar technique, there are many other sets that we could prove are countable. We already said that an infinite subset of a countable set is itself a countable set. We could show that a union of countable sets, so intersection or difference of countable set, is also countable. A Cartesian product of countable sets also gives us a countable set. And this last fact, together with the first one, we could use to prove something interesting again. So let's first show that Cartesian product of countable sets is countable. So remember, Cartesian product of sets is when you take all possible pairs when the first element comes from a first set, second element of the pair comes from a second set, and you could have more than two sets. You will still define Cartesian product the same way. So let's start by showing that Cartesian product of natural numbers with natural numbers, that is, all pairs of natural numbers, form a countable set. So with strings, we looked at strings of a certain length, and we were counting shorter strings before we were counting longer strings. Here, we will look at sum of numbers within each pair, and we will count pairs with smaller sum before we count pairs with larger sums. So let's do it. We have only one pair, well, let's start with 0. We have only one pair that's summing up to 0, that's the pair 0, 0. There are two pairs summing up to 1, it's 0, 1 and 1, 0. Three pairs summing up to 2, it's 2, 0, 1, 1 and 0, 2. Four pairs summing up to 3, and so on in general for every number n, which is the sum of two natural numbers in the pair. There will be n plus 1 possible pairs of numbers summing up to this n. And now we could build a bijection in a very similar way to the example with binary strings or with the strings over AB, by saying let's make our function output the sum of two numbers, one of which is the number of strings, sorry, not strings, but this time pairs with a smaller sum, and the second one is the index of a given pair among the pairs with the same sum, where, sometimes you could just take the first number of the pair, or maybe that number plus 1, to be that index. Okay, so the set of pairs of natural numbers is countable. How do we use it to show that Cartesian product of any countable sets is countable? Well, let's say we have a set A and a set B that are both countable. That means there is a bijection, let's call it F1, from A to natural numbers, and another bijection F2 from B to natural numbers. Now let's define a bijection between pairs where the first element is from A and second from B, and natural numbers by combining those three functions. So for every pair we assign a number which will correspond to applying the function that maps pairs of natural numbers to numbers to two, natural numbers, one of which is the result of applying F1 to an element A from a set A, and another result of applying F2 to an element B from a set B. So here I'm switching notation. Now A and B are elements of the set. They have nothing to do with A and B that were letters in the alphabet before. So this will give us a bijection from pairs of elements where the first one is from a set A, second one is from a set B, and natural numbers, provided both A and B are countable. And here's how we are going to use it, together with the property that the subset of a countable set is countable. So we already said that the set of integers is countable. You may say, what about rational numbers? Let's count them. And the way we are going to do it is by representing every rational number by a pair of integers n and m, such that this is an irreducible pair, so n and m do not have a common divisor. Moreover, let's just say if r is a negative number, then it's represented by a pair where n is negative and m is always positive. So we end up representing every natural number by a pair of integers. But pairs of integers are pairs of countable sets, and we just showed that set of pairs, Cartesian product of countable sets, is countable. Therefore, set of rational numbers is also countable because it's a subset of set of pairs of integers. This may seem surprising because between any two rational numbers, there is infinitely many rational numbers. They're very dense set. They don't really behave like integers or natural numbers, and yet we could still count them. Yet we could show that there aren't really that many rational numbers. There are just as many rational numbers as there are integers as there are natural numbers. So now it may have you wondering that it means that we could show that every possible set is countable. Is there a bigger infinity? Is there anything that's not countable? Well, there is, and there is a lot of stuff, and we will show that in the next lecture.